Solar System. The solar system is located in the Milky Way's Orion star cluster. Only 15% of stars in the galaxy host planetary systems, and one of those stars is our own Sun. Revolving around the Sun are 8 planets. The planets are divided into 2 categories based on their composition: terrestrial and Jovian. Terrestrial planets, including Mercury, Venus, Earth, and Mars, are primarily made of rocky material. Their surfaces are solid, they don't have ring systems, they have very few or no moons, and they are relatively small. The smallest and closest to the Sun is Mercury, which has the shortest orbit in the solar system at about 3 Earth months. Venus is the hottest planet, with temperatures of up to 867 degrees Fahrenheit due to an atmosphere of carbon dioxide and extensive lava flows. Next to this world of fire is a world of water, Earth. The water systems on this planet help create the only known environment in the universe capable of sustaining life. The last of the terrestrial planets, Mars, might have also supported life about 3.7 billion years ago, when the planet had a watery surface and moist atmosphere. Beyond the 4 terrestrial planets of the inner solar system lie the Jovian planets of the outer solar system. The Jovian planets include gas giants Jupiter and Saturn and ice giants Uranus and Neptune. The gas giants are predominantly made of helium and hydrogen, and the ice giants also contain rock, ice, and a liquid mixture of water, methane, and ammonia. All 4 Jovian planets have multiple moons, sport ring systems, have no solid surface, and are immense. The largest Jovian is also the largest planet in the solar system, Jupiter. Nearby is Saturn, the solar system's second largest planet. Its signature rings are wide enough to fit between Earth and the Moon, but are barely a kilometer thick. Past Saturn are the ice giants Uranus and Neptune. The slightly bigger of these ice giants, Uranus, is famous for rotating on its side. Next to Uranus is Neptune, the outermost planet in the solar system and also one of the coldest. Orbiting the terrestrial planets is the asteroid belt, a flat disk of rocky objects full of remnants from the solar system's formation.
This is our galaxy, as seen by our Gaia Space Telescope. No spacecraft can travel beyond our galaxy, so we can't take a selfie. But during its lifetime, Gaia made 3 trillion observations of 2 billion stars and other objects, giving us the best insight yet of what our home galaxy looks like. In this new animation based on Gaia data, we can identify the Milky Way's central bar and its spiral arms. We now see the galaxy edge on and can identify its bulge and disk.
It's called K2-18b.
Black holes are among the most fascinating objects in our universe. They're roughly 10 to 20 times the mass of our sun and scattered throughout the universe. There could be millions of these stellar black holes in the Milky Way alone. Supermassive black holes are giants by comparison, measuring millions, even billions of times more massive than our sun. Scientists can only guess how they form, but we do know they exist at the center of just about every large galaxy, including our own. Sagittarius A, the supermassive black hole at the center of the Milky Way, has a mass of roughly 4 million suns and has a diameter about the distance between the Earth and our sun. Because black holes are invisible, the only way for scientists to detect and study them is to observe their effect on nearby matter. This includes accretion disks, a disk of particles that form when gases and dust fall toward a black hole, and quasars, jets of particles that blast out of.
About 2 or 3 times a century, a massive star in our galaxy explodes. The star's core may survive as a neutron star or a black hole, but the rest of it rushes into space as swiftly expanding debris behind a powerful shockwave. As the supernova remnant grows, it sweeps up interstellar gas and gradually decelerates.
50 tons of space debris crash onto the Earth every day. While some debris shyly dissipate into the atmosphere, others display a spectacular light show.
2 trillion metric tons of rock is headed straight for them, and impact is less than 20 minutes away. But the rock's enormous mass is only to accelerate until it's traveling at more than 70,000 kilometers per hour. And mass times acceleration equals force. As the asteroid encounters atmosphere, friction turns it into a fireball. It takes just 5 seconds to flash through the atmosphere. The impact seems instant.
Spectacular sight must surely be this, a comet. Comets this bright are few and far between, so being lucky enough to see one is a real treat. But what exactly is a comet? Set comets apart from ordinary space rocks. First of all, they have layers. What we see here is the solid core layer called a nucleus. It's a mashup of rock fragments, dust particles, and ice. This isn't just familiar water ice, although there is some of that present. We also see exotic ices that exist as gases on Earth.
31 east side.
This is Apollo Saturn launch control, T-minus 3 hours, 4 minutes, 32 seconds and counting. Right on time as far as the astronaut countdown is concerned. The prime crew now departing from their crew quarters. 10, 9, ignition sequence start.
It's one small step for man, one giant leap for mankind. It has a stark beauty all its own. It's like much of the high desert of the United States. It's different, but it's very pretty out here. Oh, geez, that's great. Is the lighting halfway decent?
Yes, indeed. They've got the flag up now, and you can see the stars and stripes on the lunar surface.
Up now, and you can see the stars and stripes on the lunar surface.
A solar eclipse happens when a new moon moves between the Earth and the Sun, blocking some or all of the Sun's rays from reaching the Earth. By cosmic chance, even though the Sun is 400 times wider than the Moon, it's also 400 times farther away. Therefore, the two objects appear the same size in our sky.
Enter the Large Hadron Collider.
According to the Guinness Book of World Records, the Large Hadron Collider is the biggest machine on the planet.
Located at a CERN facility near Geneva, Switzerland.
The reason the Large Hadron Collider is so large is because it has one task: to destroy the smallest particles possible so we can better understand how they work.
The LHC is a really big part of them together and see what they break up into so that we understand what the fundamental building blocks of those particles are.
The protons and electrons that the Large Hadron Collider work with are so tiny that the task of making them collide is akin to firing two needles 10 kilometers apart with such precision that they meet halfway. And how the Large Hadron Collider does